What we've covered up to this point with respect to Android has been topics relating to the hardware components, some of the memory management components, and some of the operating system components. And what we're going to do now is talk a bit about the middleware infrastructure layers in Android. And so I'll start by talking about some of the middleware infrastructure, the hardware abstraction layer, the Android Runtime, and native libraries, which are all part of this set of layers. And you'll see that this middleware infrastructure resides atop of the Linux kernel, the Android Linux kernel, but below the applications and application framework. So it's kind of in the middle, which is why it's middleware. We'll see that there's other pieces of middleware too, but this is the infrastructure parts. And you can also see that the bulk of, well, I shouldn't say the bulk, a lot of this code is written in C and C++, although the core libraries are written in Java. The color coding here is basically, the stuff in red is the kernel, and that's all written in C. The stuff that's green is typically C++ with a little c, and the stuff that's blue is typically Java. So the middleware infrastructure layers responsible for providing reusable capabilities that extend the hardware-centric OS kernel stuff that's provided by the Android Linux kernel, and of course all the protocols that are buried down there to do internet protocols and the binder driver that sends messages back and forth between processes on the same machine. So the first part of this is something that's called the hardware abstraction layer, or the HAL. And the purpose of the HAL is to shield the Android stack from low-level hardware details. Now, the funny thing here is when you hear this, your first inclination should probably be, well, wait a second, isn't that what the operating system kernel is supposed to do? Because after all, the operating system kernel is also a hardware abstraction layer, if you think about it. And the main difference is, well, there's two differences. There's a technical difference because the kernel shields you from hardware using low-level device driver APIs written in C, which are tedious and error-prone to program, whereas the hardware abstraction layer provides some shielding of these mechanisms using more object-oriented C++ APIs that also do things that are not typically provided by out-of-the-box GNU Linux kernels. So there's things that's provided up here with respect to things like the radio, the cellular phone, GPS, some other more advanced forms of cameras and audio devices, and so on and so forth. So those kinds of things are not typically provided out of the box with GNU Linux, but they are provided by Android Linux because it's a mobile device operating system after all. And so they wanted to provide a more object-oriented way of accessing those things. The second reason that they have a hardware abstraction layer has to do with the licensing regime that's used in Android. So I think I mentioned this before. Everything that's in Linux is supported using or is licensed using the GNU public license, the GPL. And that comes with some strings attached. Most notably, if you're writing device drivers in the Linux kernel, you are obliged to make your device driver source code available in open source form. That's sometimes called virality, which means that if you use the GPL, then it virally will infect everything that you do if you use the GNU public license. And for that reason, the idea was to provide another layer of abstraction, the hardware abstraction layer, that would not be subject to those, let's call them overly permissive, from some people's point of view, overly permissive perspectives on licensing. So the hardware abstraction layer's license is a so-called Apache-style license, which says the source code is open, but you are not obliged to give away your source code if you link with our APIs. And of course, a lot of the OEMs, original equipment manufacturers like HTC, Samsung, LG, Acer, Asus, the list goes on and on, they don't want to give away all of their code because that's their competitive edge versus the other manufacturers. So this was a deliberate choice made to incentivize OEMs to use Android without having to give away all of the secret sauce that differentiates them from their competitors. There's also a runtime and libraries layer, which is a layer that's composed of a couple different middleware elements, as you can see, with the different colors that are shown here. So we have this thing called the Android Runtime, which is called sort of a sub-layer, I guess, or a partition. And it's composed of two parts. We have something that's called a managed execution environment that will run Java-based apps and some Android system services that might be written in Java. And there's two variants of this. One is the Dalvik virtual machine. Dalvik has been around since the beginning of Android. It's a variant of the Java virtual machine that uses a register-based model rather than a stack-based model. Don't worry too much about that with respect to its bytecode. And comes along with a just-in-time compiler and has different bytecode format than the Java virtual machine, but plays a similar role as the Java virtual machine. It interprets the bytecodes. And that was there originally because when Android first came out, they were trying to get all this stuff into a small footprint device or devices with 200 megabytes of memory, and interpretation was perceived as being more efficient. That turns out to be a time-space trade-off, as you would undoubtedly learn if you took certain compiler courses or runtime courses like the programming languages course here. And so later, about 5 releases or so, I think it might have been Android Lollipop or Marshmallow or whatnot, they moved to something that was a way ahead of time compiler. Instead of a just-in-time compiler, it's a way ahead of time compiler. And it's called ART, which stands for Android Runtime. And so this is a compiled solution. So they take the Java code and they compile it into native code as opposed to bytecode. And so it typically is a lot faster, even though it might be bigger. But by the time they did this, devices had gigabytes worth of memory as opposed to hundreds of megabytes worth of main memory, so the time-space trade-offs made some sense. There are still some vestiges of Dalvik lurking in parts of Android, but by and large, a lot of it's been replaced with ART. And ART and Dalvik are written in C. And of course, they optimize it for mobile devices. There's also, I think I mentioned this before, a copy of the core libraries that come with Java, Java TM, right, the standard Sun/Oracle Java, as well as a bunch of core Android class libraries that do other kinds of things. And we'll talk some more about that later. One of the key things that we care about in this layer, of course, is threading. So we'll talk more about this, but that's obviously a big part of this class. So all the stuff we've been talking about with respect to Java threads and the executor framework and all those synchronizers we've been looking at, that stuff all lurks up here, up to Java 8. Java 9, 10, 11, other versions of Java are not yet supported with Android. They may or may not ever be supported. But for our purposes, Java 8 was what was important, so that is indeed supported as of, again, 3 or 4 releases ago. The other things that are provided in the Android core libraries, this is part of the Android part, not the Java part that was copied from Oracle, are these various components, and we'll talk a bit more about them later. So things like activities, services, broadcast receivers, content providers, and intents, which glue together activities, services, and broadcast receivers. And these abstract various roles that are important for writing Android apps. So we haven't really spent a lot of time on writing apps in this class, but were we to do so, you would see that a lot of stuff is based on activities, which are the user-facing elements that interact with the user through input and output dialogues or key handlers and stuff like that, click listeners. There's services, which can run in the background like a little daemon and do things that may take longer to run that you want an activity to be aware of. We have these things called broadcast receivers, which are basically a pub-sub mechanism that allow one part of the system to send out an event, say when the battery gets low or the phone becomes available because someone disconnected and so on. And then other parts of the system can subscribe to those events and do something about it, like notify the user or flash the screen or whatnot. And then intents are these little messages or events that get sent around to activate components or to indicate that something's occurred. And then something else that's important is a content provider, and all the things in the system that need to store data in a structured way are designed with content providers. And a content provider typically, not always, but typically provides a wrapper for the SQLite database, which is a variant of SQL that's optimized for smaller footprint devices. Okay, if this was a class on Android as opposed to a class on Java concurrency in the context of Android, we would spend a lot more time on all of these things. And in fact, if you're curious about this stuff, I have a MOOC that goes through all these things, and you're welcome to watch those videos if you're so inclined. There's also other stuff that comes with Android. There's things that do user interfaces, all the ways that you interact with the system, dialogues, here's the SQLite stuff, 3D graphics, 2D graphics, persistence, blah, 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 lots of stuff that's provided in the Android runtime. And this is where you can find more about that MOOC I was telling you about. We did this a couple years ago. And Android's changed a bit since then, but the bulk of what we cover there is still relevant. So one of the things that Android tries to do, just like Java tries to do, is provide a balance between programmer productivity, in other words, how easy is it to write apps, and runtime performance. Now, you could obviously maximize performance by writing everything in assembly code, right? Or writing everything in C, or writing everything in C++. But experience has shown us that those languages are tricky to program. If you're a really good systems programmer, it's not that bad. But if you're more of a garden variety application developer who's taken some MOOCs or some courses on Udacity or whatnot, C++ and C, or assembly code, for God's sake, is just way, way, way too complicated, and life would be miserable. So it's a trade-off. One thing I will also mention as part of this trade-off is that the Android design uses lots of so-called native methods, and we'll talk about what native methods mean in a second, but that's how they get some of the performance. A lot of the APIs for app developers are designed with Java, but then the implementations of those methods are not necessarily always written in Java. They're often written in C or C++. So you kind of get the benefits of Java-like abstraction, which is really cool and high level, with more efficient performance. And that was really important back in the early days of Java, or early days of Android, when they were much more limited in terms of memory, in terms of processor speed, and so on. And that's the point here. The core libraries are often implemented as wrapper facades, which is a pattern I wrote decades ago that just talks about how you provide higher-level object-oriented interfaces to low-level C functions. And those low-level C functions typically come out of the native libraries. So there's a bunch of native libraries that come along for the ride. I think pretty much every one of these things is open source. So you can download the source code. If you download Android, you'll see that there's a whole giant tranche of these libraries that are available there. So a lot of these things have an existence outside of Android. SQLite, libc, SSL, WebKit, these are all things you're likely to stumble upon in other ways. OpenGL, very popular framework for 2D and 3D graphics. If you take our graphics course here with Bobby Bodenheimer, you probably get exposed to that one way or another. And then some other stuff that's more Android-centric. So how do you, display things on the surface of the touchscreen, various multimedia frameworks so that you can play videos and audio in the background, and so on and so forth. And these capabilities are available in something called the Native Development Kit. And it's possible to write entire apps with the NDK. Probably not that common for most apps. Maybe for some gaming apps you might do this, because you really need to get ultimate control and ultimate performance. But nowadays, as I mentioned before, with Java and the hardware getting more efficient, it's really not that necessary. Okay, so that's the end of the discussion of the middleware infrastructure layers in Android.